Alright, pre-calc students, welcome to the video which is going to take you through very quickly, hopefully, parametric equations for parabolas, circles and ellipses. A little bit of business before we get started, and so in this particular note, so this is the note on lesson 8.5, you need to change example number 2 so that it reads x of t is equal to t plus 1. And then what you also need to do is go down to your practice problems for 8.5 and make a change to question number 3. Make sure that it's x of t equals t minus 2. This is just to ensure that the problem has got a layer that we want you to be aware of, and I'll talk about that a little bit later. Okay, next important thing, what I'm going to do is I'm going to skip over some of these examples, and a couple of times what I might do is you'll see on the right hand side I've got some solutions just to try to be efficient with the video. I'm going to enlarge the document on the right occasionally just to show you some solutions, just so that we can expedite the the process of getting through this without it taking too long. Okay, along those lines as well, what I've done is I've circled the questions that I'm going to answer. So nothing wrong with example 1, but all the conceptual ideas from example 1 are kind of explained in example 2, and what I'll do as necessary maybe is just touch on those elements of the examples that aren't dealt with in some others, and we'll try to make sure that you get a complete conceptual picture. Okay, so the one of the really big takeaways for you to understand as we move into parametric equations for parabolas, circles and ellipses is that the ideas are exactly the same as parametric equations for lines. And so essentially what that means is when we were dealing with lines in a previous unit, we linked that equation of that line to a parameter, usually time. What that did was when we restricted the time domain, it restricted the domain of the rectangular graph, which means our line became a line segment. And what we were also able to layer on top was for instance, if the line represented a particle, we were able to layer on top the position of the particle at different times, and along those lines we were able to model, therefore, once we knew time and starting point, what direction the particle was traveling in. These conceptual ideas are identical for this lesson on parabolas, circles and ellipses, and so that's a really big important point for you to keep in mind as we move through this. Okay, very first example, the warm-up question. This one excuse me, is based on parametric equations that model the tracing of a triangle. I'm going to skip over this because you have already got a video that will take you through this, and so what I want to get straight into is example number 2. Okay, so first things first, we've got a set of parametric equations, x of t, y of t, both obviously defined in terms of t, and the difference here is that you'll notice that the y of t is now quadratic. Okay, and so hopefully what you're thinking, if you were paying attention before, is that we must be dealing with a parabola, and as I mentioned before, all we're doing when we restrict the time domain and layer time on top of the rectangular equation is typically what we're interested in doing is graphing a piece of the parabola with a defined starting point and a defined direction. Okay, that said, we're going to start this first example by using a table of values, and again, table of values, not always the most efficient method, but a pretty fail-safe method which you can go to if you're out of other ideas. Okay, so what I'm going to start off with is writing down integer values. Of course, life doesn't always work in integer values, but of course these examples have been structured so that for the purposes of making it clear what we're doing, the integer values are going to yield what we need. Okay, first things first, I've selected integer time values from my lower end of my domain to the upper end of my domain. I'm now, for the x of t, going to focus on the relationship between x and time, and the corresponding x values for time equals 0 will be 1, 2, 3, 4, and 5, because of course the relationship is x is equal to time plus 1. What first kind of, or rather next really important point, is for you to understand that the relationship that x has to time is not the same as the relationship that y has to time. And I'm going to plant that seed now because it's going to be important later. If we make a modification to the xt equation, or we make a modification to direction, the way it affects x is not the same as the way it affects y. Okay, so what you need to do with that, just put a pin in that for now, and we'll come back to that. So y of t, a very common error, of course, is to substitute x values in to find these. That is, of course, an error. The y relationship is with respect to time, and so in order to find the y values, I'm subbing in the list of time values, not the list of x values. Okay, so subbing 0 in here is going to produce 0. We sub 1 in, that is going to produce minus 1. And then what do we have? We've got 0 again. This time I'm subbing t equals 3, so I've got 3 squared is 9, minus 6 is going to give me 3, and lastly I'm going to sub in 4 squared, 16 minus 8 is going to give me 8. What you can see here is what we have is a rectangular graph, and so what we're going to be able to represent on this graph is, of course, the relationship between x and y, and then we'll layer on the element of time after the fact. Okay, and so I'm going to start off by plotting those points, and so we've got the x value of 1 for the y value of 0, okay, x is equal to 1, y is equal to 0, x is equal to 2, y is minus 1, x is 3, and we're back at 0, x is 4, and we have y at 3, and lastly x is 5, and we have y equal to 8. And hopefully what you realize is we have now got a piece or a section of a parabola. Okay, what we should be able to do also is to make this connection that time is increasing from 0 to 4, and at the start of the domain at t equals 0, the x and y value, the corresponding x and y value are 0, 1, and so that allows us to know that that is our starting point. The starting point is at x equals 1, y equals 0, and in this particular context, given that it's a parabola, there's only one direction since we know where it started, and so we can layer on our direction. Okay, so that's the parametric piece. It's done 3 things for us. It's told us effectively by limiting time, we're limiting the rectangular domain, we are able to identify a starting point, and then we're able to identify the direction of motion. Okay, so now what we want to do is we want the curve to be traced in the opposite direction. Okay, and so this is going to be, this is typically one of the more confusing elements, and so what I'm going to do is I'm going to sketch, so we'll take a minute or two to make sure that this is clear, or as many minutes as we need. And so what I'm going to start by doing is, first of all, be clear that this is an xt graph. This is not an xy graph. This is the relationship between x and time, because of course with x and y we don't have direction, we don't have that layer of time, and so opposite direction has to do with modifying time's relationship with x, or y is possible as well. Okay, and so we're going to start off, and what you can see from our graph is our original graph starts at t equals 0 and x equals 1, and so we have this point over here, time is 0, x value is 1, and at the end of the domain we had t equal to 4 and x equal to 5. So I'm going to just give an approximate plot of that. This is time 4, x value 5, and I'm going to join those two. Okay, that was our original x of t relationship, x of t equals t plus 1. Okay, what we're now going to do is try to address this idea of moving in the opposite direction. And so if you look carefully at the graph, we started at x equals 1, and we finished at x equals 5, and we want to reverse that. In order to reverse that, essentially what we need to do is we need to have this as our starting point and change the direction. Okay, and so what that basically means is we need x equals 5 as the starting point, and that starting point must correspond to time, because you'll notice we're not modifying the domain at all. And so what that essentially amounts to is at time 0 for the modified equation, at time 0 the x value should be 5. And similarly, at time 4, the x value should be 1. And what that will result in is us reversing the direction of the graphing, having the starting point change to the x maximum of 5 and move to the x minimum of 0. Okay, and so now we can rewrite our set of parametric equations. You can do this in terms of reflections. It might help you to understand this. In this case, I'm going to keep it a little bit simpler, and we're just going to focus on what is the equation of our new xt relationship. Okay, and so you can see we have what we would traditionally call a y-intercept. Of course, it's an x-intercept now because the y-axis is the x-axis, because it's an xt graph. And so we have x equals 5 minus t. That's a y equals mx plus b equation. I've started with the y-intercept and I've figured out the slope. 4 minus 0 is going to be 4. 1 minus 5 is minus 4, and that confirms we have a slope of minus 1. My x graph, parametric graph is going to be x of t equals 5 minus t. The next thing we need to figure out is what is y of t. And what you should realize is that that is y's relationship to time. We've just modified x's relationship to time. And what we cannot assume, as I mentioned before, what we cannot assume is that a change in the relationship between x and time will result in the same change between y and time. And so we have an expression over here. So let me just clean that up. We have an expression here for the relationship between y and time before it was modified, and that doesn't help us because right now we only know what the relationship is between x and time. And so what we're going to do is we're going to convert the yt equation to a rectangular equation, and that way we'll have a relationship from x to time, from y to x, and that'll allow us to find our relationship y to time in the modified graph. Okay, so we're going to do that in the same way as we always do. If x is equal to t plus 1, then t is equal to x minus 1. If I then make that substitution into the y of t equation, it then becomes the y of x equation, and that is the rectangular equation. And so essentially all I've done is I've eliminated the parameter in order to find the rectangular equation. That will help me because I can now make a substitution of my modified xt relationship, and I can make that substitution in to the rectangular equation so that I can connect the change in time with x to the change that the time has on y. Okay, and so my y of t equation now becomes 5 minus t in the place of x, minus 1 squared, minus 2 times 5 minus t in the place of x, minus 1, and I'm just going to clean that up just the tiniest little bit. 4 minus t all squared minus 2 times 4 minus t is the modified y equation, and you can leave it in that form or you can distribute it out either way. Okay, so just to recap, all we've done is we have sketched a piece of a parabola because we related time, and time was limited, which limited the x domain, which meant we had a piece of a parabola with a defined starting and ending point and a defined direction, and then we reversed the direction by considering the relationship between x and time, and then going through the rectangular in order to connect the change in time to y as well. Okay, let's move on. So example 3, I've circled it. I'm going to come back to it, but just parts C and D, just to explain those elements, because I think there's going to be a little more value in doing example number 4. Okay, so we've dealt with a parabola. If you take a careful look at the trig graphs over here, and you look at the amplitudes, that might give you a small indication that what we're after at this point is the equation of a circle. So this is going to be a circle that is being parametrically represented. You should be able to realize that because the x values are going to oscillate between, we're starting at 2 and we're oscillating to a maximum of 5 and a minimum of -1. The y values are going to oscillate between 3 and minus 3, and so hopefully you realize rectangularly the shape that has a radius of 3 is of course going to be a circle. Alright, if that connection is not obvious for you, then what I'm going to show you is we're going to make that connection graphically, and this would be my suggestion to you dealing with any parametrics with a trig function. In my opinion, the easiest way to understand them is to sketch yourself an xt graph with your trig function represented. Okay, like I mentioned, we have got a center line at 2, we have got a maximum for x of 5, and we've got a minimum of minus 1. Similarly for the y, this is our yt graph. We have got a y maximum at 3, a y minimum at minus 3, and our center line in this case at 0 is our t-axis, so this is still an xt graph. And we're going to start off by sketching those. So we have 3 sine t plus 2. So regular sine graph starting at the center line. And we've completed a single cycle of the graph given our domain. Similarly, minus 3 cos of t, that's the negative cosine graph. It'll start at the minimum up to its maximum and back down to its minimum given our domain. Okay, and now if those two graphs, which is hopefully some kind of presumed knowledge and stuff that isn't confusing you too much, we can now start to make the connections to the rectangular graph. And so first things first, as we did with the parabola, at time 0 is going to be our starting point, and at time 0 we have got an x coordinate of 2, and we have got a y coordinate of minus 3. Okay, and so if I go into the graph, obviously this is a rectangular graph xy, so we don't represent time, or at least time is not one of the variables represented, and so we need x equals 2, y equals minus 3. Okay, and so I'm going to go to 2 minus 3, and the point 2 minus 3 is going to be the starting point of our graph. The other connection, hopefully, that you can already start to see is that the y value is at its minimum, which is minus 3, and so we're expecting it to go up to a maximum of 3. The x value is starting at its center line of 2, and it's going to oscillate to a maximum of 5 and a minimum of minus 1. Okay, and so again, if that's not particularly clear to you, then let's look at the next point along the sine graph and also along the cosine graph, so the xt graph and the yt graph. At pi over 2, the x value has now reached its maximum of 5, and so that allows us to know that 1, 2, 3, 4, 5, we have then moved from our starting point to our maximum x value, and we can confirm that at pi over 2, of course, the numerical value of y is going to be 0, and that's confirmed by the point that I just plotted. As we move through the graph, the next key point that we're after is the x at pi. X is going to be equal to 0, I beg your pardon, and y is going to equal its maximum value of 3. That, of course, is going to correspond to this point over here on the graph. X equals 2, y equals 3, and then hopefully by now you are making the necessary connection, and you can see what we're talking about is a circle. The circle center, if we wanted to find the circle center, would be at x equals 2, y equals 0, and I'll show you how we can get that rectangularly as well. We've got our starting point, and we also ascertained that our second point was the point 5, 0, and so let's complete our circle first. And just move that into place. Close enough. Okay, and so we've got our starting point, and we've also determined that our direction in this case is going in a counterclockwise direction. And again, just to reconfirm, we were able to know that because we started at x equals 2, and then we moved to the maximum x, and so x equals 2 was our starting point, and then we move to the maximum x, which indicates we must be moving in a counterclockwise direction. Okay, though that is the really big idea in this example, and the idea I've just highlighted is going to be identical when we then deal with an ellipse. Okay, let's just deal relatively quickly with the other stuff. And so we are eliminating the parameter by using our by using our Pythagorean identity. And so if x of t equals 3 sine t plus 2, then sine of t will equal x minus 2 over 3. Similarly, cos of t will equal y over minus 3. And if we use the Pythagorean identity, we know that x minus 2 over 3 all squared plus y over minus 3 all squared is equal to 1. Of course, x minus 2 over 3 represents sine of t, and y over minus 3 represents cos of t, and so that's sine squared t plus cos squared t equals 1. And then we can rearrange this into the form we're probably more familiar with. And of course, when I square the minus 3, it becomes 9. Both of them are on top of a denominator of 9. Cross multiply, and I get x minus 2 squared plus y squared is equal to 9. Again, confirming the center of our rectangular circle is in fact at 2, 0, and we have a radius of 3. Okay, which is pretty much what we were expecting. And so in order to get the rectangular equation, we eliminate the parameter, and the way we do that with trig functions is via the Pythagorean identity. Okay. Of course, we could have also just read that off the graph. All right, so now same conceptual idea as we were dealing with the parabola, the idea of the change of direction. Fortunately, with circles and also with ellipses, it's a little bit easier because we are just going to be using the trig graphs in order to do that. Okay, so once again, what I'm going to do this time is I'm going to just relatively quickly resketch my XY graphs because we're now going to modify those graphs. So new instruction, suppose we want to trace the curve. Domain is unchanged. We want the starting point to be 5, 0. And so we're tracing the same curve, the implication being we're also going in the same direction. And so we want the direction to still be counterclockwise. The difference now is we want our point here on the graph. This is going to be our new starting point. Okay, and so we want a new starting point of 5, 0, and we still want a counterclockwise direction. Okay, and so now what we're going to see is what effect that has on the graph. Okay, so the x's, nothing has changed in terms of the fact that we still have a center line at 2, and we still have the graph oscillating from a maximum of 5 and a minimum of minus 1. Similarly for y, we still have maximums at 3 and minus 3 as the minimum, and the center line at 0. And we are still drawing an xt and a yt graph. Okay, now let's deal with what we need. First of all, we need the x coordinate of the starting point to now be 5. What that means is effectively we are changing the xt function to the cosine function in order for it to start at its maximum. Okay, and then of course we complete one single cycle because our domain is unchanged. Let's figure out the corresponding impact on the y. The y value now has a starting point at 0, and this is going to be really important now because in order to maintain direction, so we need to look at the graph, the y value starts at 0, and because we're moving in a counterclockwise direction, we can see that what y does first is go to its maximum as opposed to going to its minimum if it were clockwise. So it goes immediately to its maximum. That means graphically this is what's happening, and that of course very easily is identified as the regular sine graph. And so now we can write our modified equations. X is going to have the same amplitude, so it's still 3 cosine t plus 2 because of the shift up to the center line. Y of t in this case now becomes 3 sine of t to account for the fact that it's starting at 0 and going to a maximum. Okay, and so that is how we're going to be able to modify the starting point. And of course we were not asked to modify the direction in this case, but we very easily could have, had we had y go down instead. A negative sine graph would have allowed us to model instead in a clockwise direction. Okay, quick connections that I want to make up in example number 3. And so what I'm going to do is just drag the solution to example number 3 over here and just show you the important part here. So this again, you've got x of theta this time. It doesn't really matter whether it's x of theta or time, just pay attention. Parametrically it's the same conceptual idea. And so we've got both of those with amplitudes of 2. That implies a circle. This particular circle is centered at the origin, and so if we go down here, so all of the rest of the example is the same. What I wanted to draw your attention to was this. So what would happen if we changed the domain of the parameter from 0 to 2 pi instead from, beg your pardon, 0 to 2 pi instead to 0 to pi? What you should be able to realize, of course, is that means if my original function was the cosine function, 2 cos theta, if we only graph until pi, we are only graphing the first half of the trig function, and so the connection that you need to make is that only the top half of the circle would have been graphed by us limiting the domain. Second element that we can consider, since we're talking about position and we're talking about time, we can consider the idea of speed. What if I wanted to trace the identical circle, but I would like to trace it twice as fast? And so if we want to move twice as fast, of course the other way we can do that is to modify the trig graph once again to make sure that it completes an entire cycle instead of in the regular 2 pi. If we wanted to complete the entire cycle in pi, that would allow us to graph twice as fast. And of course the way that we do that is to modify the period or increase the frequency, which of course increases the speed. If we want to trace the graph over exactly once, we also need to restrict our domain. And so had I not restricted that domain,